Welcome, everyone. Thanks for coming. It's a great occasion and a great excuse to be all together here in this room. Rachel, thank you for giving us that excuse. So just very quickly, I just want to give the mic to Rachel so that she can do her show. Just say a couple of things. The first one, let's see. So in my head, there's two kinds of people in robotics. There's like the kind of people that over time, they get very excited about algorithms and information flow. There's many of those people today. And there's the kind of people that get excited about atoms and friction. And when Rachel started in 2017, I said, okay, well, which kind do you want to be? And I think we all know that Rachel has problems deciding. So she said, let's just try to be both. And one of the things that I'm very excited about Rachel's research is that it's right in that middle. It's right, sort of, it has that special thing that you can only get when you sort of, your mind starts to think both about algorithms and friction. And just makes a very interesting story. So which I'll just let Rachel explain. The second thing that I wanted to say about Rachel, and which I'm sure you all know, but we all have to acknowledge in front of her, is that Rachel has an incredible commitment to service and to helping people, and that makes her very special, right? So all the way from her sort of involvement in high schools with high school students, all the way up to faculty search committees, right? It's just incredible. What is Rachel doing in a faculty search committee? So again, she has trouble saying no and deciding which things she wants to do, and because it's very close to her heart to always be helping people, she's been involved in so many things at MIT that a big part of sort of the things that many of us in this room we've sort of benefited from, it was in part because of Rachel's effort. In my lab, of course, like she has been sort of a mentor, a helper, a facilitator to many things, both technical, setting up sort of robots, making sure that many people in the lab could use robots, knew how to use robots, and quickly, as everyone realized that Rachel is great at doing that, sort of expanded towards many other labs. Or other things just like more social interaction, right? Like just facilitating, always making sure that when someone's birthday was coming up, there was a birthday cake on the table and a knife to cut it into enough slices. So that's the kind of person that Rachel is. Incredibly technically strong and interesting, but also sort of like that core of personality that makes her an amazing person to work with. And I'm extremely happy to be here, that you made it to this day, and even more excited for what's coming. Thank you, Rachel.
Okay, so is the mic connected? Okay, I was most nervous for Alberto's intro, so it's smooth sailing from here. So hi, thank you everyone for coming, both over Zoom and in person. And so I want to jump right in and say that like my goal always has been and always will be that I want to enable robots to do things like cook dinner in the home, to clean up messy classrooms, and to pack supplies in hospitals. And to think about what a robot needs to do in order to accomplish these types of tasks, we're going to look at one illustrative task, specifically asking a robot to cook stir fry, and we're going to think about doing the first step in the recipe, which is chopping vegetables. So let's say that we have our robot here, we have a knife, and we're going to chop cucumbers. I like cucumbers in my stir fry. Sometimes it's the most controversial thing I say. So we're going to cut cucumbers, and we think about what does it take for a robot to cut a cucumber? Well, I'm going to frame this as that the robot first has to determine a sequence of actions to complete the task. And to cut a cucumber, you can imagine that our robot is going to maybe grasp a knife, move the knife to the cucumber, and then slice the cucumber. Because we want the robot to execute this in the real world, it has to solve for the parameters of these actions. And these parameters are discrete and continuous and have constraints. So for example, we can imagine in order to grasp the knife, we have to select how are we going to grasp the knife, but do so in a way such that we can reach that grasp and so we can exert enough force to actually slice through. If we're going to slice the cucumber, we have to, for instance, decide what forces are we going to exert and how is the robot going to exert these forces. And many, if not most of these parameters are continuous. And so given this, we can think for this strategy, can the robot find a satisfying set of these parameters? Can the robot succeed in accomplishing the task with this given strategy? I'm going to lead the witness slightly and say that if the robot were to accomplish this sequence, that when it goes to cut the cucumber, because nothing's holding it in place, it would roll around. Trust me, I've done it. And so in this case, we'd say that that is bad. We don't want that to happen. And so I'll say that the robot in this case would fail because it is violating a constraint of holding the object still while we are slicing it. So what I want my robot to do is to now find a new strategy, namely one that secures the cucumber in place before cutting it. And if we look at the environment, one way that we could do this is that our kitchen has a vise. And so we could ask our robot to find a new sequence where we're going to grasp the cucumber, place the cucumber in the vise, close the vise, grasp the knife, move the knife to the cucumber, and slice the cucumber. And again, we'd have to solve for the action parameters. And it would be all the parameters from before, as well as additional ones like how do we grasp the cucumber and where do we place the cucumber within the vise. So you can ask the same question from before, would this succeed? Well, in this case, we have this blocking object that's sitting on top of the vise, and what this means is that there does not exist a collision-free pose for the cucumber in the vise, and so we cannot place it there. So again, this strategy would not succeed, and our robot has to find a new sequence. So here we can imagine that the robot's going to grasp the red block, move it somewhere, anywhere, and then continue the strategy from before. Again, will this succeed? Okay, this game is fun, I could play it all day, but third time's the charm, and in this case, yes, our robot is able to succeed. It's going to grasp the red block and move it anywhere, just as long as it's out of the way. Once it's done that, it's going to go over and grasp the cucumber. The vise is part of the system, so it is the robot's responsibility to open and close it. And once it's done that, it's going to go grasp the knife. Oh, this gets people. It's a real knife. I do intend to actually cut cucumbers. So we're going to grab it and actually cut the cucumber. Great, success. Good job, robot. So in this case, I framed this as that the robot had to solve for what is the sequence of actions and what are the parameters of those actions, and those choices impacted each other as well as being impacted by the constraints of the task and the environment. And you know, good job, robot. I'm glad it accomplished this task in this environment, but really, I want my robot to be able to accomplish many tasks in many different environments. And so it's important that the robot's behavior is able to generalize. And in order to generalize, I would argue that the robot has to do the type of reasoning that we walked through. It has to be able to reason over how do I satisfy all of these constraints across this hybrid combinatorial search space, accounting for the environment and the task. And because of this, I adopt a model-based approach that we will empower the robot with models of the world, which could be come from engineering mechanics or could be learned, but the robot is going to reason over the models. And this is because I think if we prescribe the robot exactly what to do, that will struggle to generalize. And so I want the robot to be responsible for the reasoning. So given that we're going to take this model-based approach and we're solving a hybrid combinatorial search problem within robotics, this is often framed as something called task and motion planning, or TAMP. Now, my lab mates and I wrote a survey paper on this a few years back, and there's been a lot of really lovely work in task and motion planning, but the overwhelming majority of it, with one kind of limited exception, has been focused on reasoning over constraints related to geometry. And what I mean by that, and I guess this hints towards Alberto's introduction, is that it's reasoning over, is a motion collision free, is a placement free? Now, no shade, this is still an incredibly hard problem. You have to reason over, especially if you're dealing with kind of confined environments or a lot of objects or long horizon. But I'd argue that this is fundamentally limiting if you're only reasoning over geometry. And this is why a lot of task and motion planning demos often look like pick and place. Because if we think about the kind of tasks that I started the talk with, I would argue in order to solve these types of tasks, our robots have to reason over both geometry and physics. We saw in our example how the need to exert force changed how we had to secure the object. You can also imagine if we're swinging a hammer, if we're packing dough, that all of these are going to impact our robot's decision-making process. And so the main thrust and kind of goal of this thesis is that we're going to be proposing models and algorithms that enable the reasoning over geometry and physics in the context of these multi-step manipulation problems. Now, giving an outline for where we're going to go, I'm going to start off by thinking about how we can plan for this multi-step manipulation, and specifically kind of focusing on where we're considering force and motion. I've kind of already highlighted why that's particularly important. We're going to start off in the context of a body of work we call forceful manipulation, and then we're actually going to do a detour within that to talk about in-hand manipulation. Throughout all of this work, we're going to be proposing new and leveraging existing models. We're going to verify that those models hold in the real world. But as we get into kind of messier and messier manipulation, that might be difficult to have such certain models. And so in the back half of the talk, we're going to focus a bit more on handling uncertainty and particularly defining models that kind of capture the inescapable uncertainty and algorithms that have to reason over it more explicitly. And to do this, we're going to revisit the forceful manipulation, thinking about how we can be robust to uncertainty in our parameters. And then we're going to think about how we can plan non-prehensile dynamic manipulation where we have action uncertainty. So this is our plan so far. Comments, concerns, questions. Okay, so we're going to dive right in. And I want to think about what we're calling forceful manipulation. And the way we're going to frame kind of this section of the talk is we're going to think about how forces impact, pun intended, our planning decisions, how we can capture and model those forces, and then how we can integrate that model into an existing state-of-the-art task and motion planning framework. And the running example throughout much of this talk this section of the talk is going to be opening a push-twist child-proof bottle. And so this is a bottle where in order to open it, it's my favorite thing, is that you have to both push down the cap and twist. And so we'll think of this as that you have to exert both a downward force and a torque about z. For now, we'll assume these quantities are given, but later on in the talk, we'll think about how we can relax this assumption. And so if we want to open the bottle, here is an instance of the robot doing that. It exerts that kind of push-twist on the cap of the bottle. And then once it's done that, it can open up the bottle. And the bottle is rice. There's actually no pills. Okay, so the robot has done this, and we can think about, how does the need to exert force, how does that push-twist action impact our robot's decision-making? And in the first way, we kind of already saw in the cutting example, which is that if we're going to exert force on an object, we have to hold it still. And to kind of prove that here, we do not hold the bottle still. It slips relative to the table, and so we are not able to kind of successfully exert our push-twist, and we go to open the bottle, we do not succeed. And so this is to say that if you're going to exert force on an object, you have to hold it in place. You have to, the environment, either through objects or the robot has to hold it in place. I'll note that the reason it didn't slip before is because in this video, the object is sitting on a high friction surface that's effectively holding the bottle in place. And so I'll refer to this as our fixturing constraint, that you have to hold the object still. That's the first way that forces impact planning. And the second way is that if we're going to exert a force, I'm going to say that our robot has to be strong enough. Now, to explain what I mean by that, we're going to do a dive into mechanics. So I'm going to view the entire system while we're opening the bottle, so including the robot, the bottle, and the table, as one kinematic chain. And that kinematic chain is formed of a series of joints. And some of those are robot joints, and some of those are frictional joints formed via contact, for example, the robot's grasp on the bottle. And the constraint that needs to be true, what needs to be satisfied in order to successfully complete this task, is that we'll say in the face of the exerted wrench, the force and torque experienced during our push twist, is that each of the joints within our forceful kinematic chain needs to be maintained. Each of our joints needs to be able to resist the wrench. Now, in order to capture this, what we're going to do is we're going to mathematically model the amount of force and torque that each of our joints can resist. And if all of our joints can resist it, we'll say that each of our joints satisfy the constraint and our overall train is stable. Yes, I'm misusing the word stable. Okay, so to map this through, let's think about our different types of joints and how we can capture how much force and torque they can resist. And I'm actually going to start off with I'd argue, the easier case, the more straightforward case, which is thinking about a robot joint. So robot joints have torque limits. They're limited in the amount of torque that you can exert. And so breaking that joint or violating that constraint would correspond to the robot hitting a torque limit. It makes a very sad noise. We want to avoid that. So how do we capture if we're within our robot's torque limits? So what we need to do is take the force torque experienced during the task and transform it into torques experienced during the joint. And so the way we're going to do that transformation is we're going to take forces and torques called wrenches experienced in the task, transform that into the frame of our hand, our end effector. This is a rigid body transformation. And now we need to transform it into torques at the joint. And the way we're going to use that is an operation called the manipulator Jacobian. So if you take the forward kinematics of a robot and differentiate it with respect to time, you get the Jacobian. And the Jacobian maps joint velocities to end effector velocities, and beautifully, I think, the transpose of the Jacobian, which is what we have here, maps end effector wrenches to joint torques, which is exactly what we're looking for. I'll note that it's parameterized by our joint angles, our configuration Q, and intuitively you can think that this makes sense, because if you think about your own arm, there may be certain configurations where you can resist more or less force, and our configuration-dependent Jacobian is capturing that. Okay, we use our Jacobian, we transform into joint torques, and then we can compare to check if we're within our robot's torque limits, which we'll assume we have known. And we can actually do this for all of our robot joints, evaluating if our joints satisfy our constraint. Great, these are our robot joints. We have another type of joint that we're considering, which is our frictional joints formed via contact. In this case, we actually have two examples, one of which is the bottle's contact, the robot's grasp on the bottle, and the bottle's contact with the table. And we'll say that for these types of joints to break happens if the two objects move relative to each other. And so we want to think, are these joints stable? The question is, what type of motion is achievable for this type of grasp, this type of joint? Well, I'll observe that both of these are planar joints, and to explain what I mean by that, we'll look at one in particular. And so if we zoom in on the contact between the bottle and the table, what I will argue is in 3 dimensions, the bottle cannot move. This is because we're going to assume we have rigid bodies, and so we cannot rotate or go into the table. And so we will assume that in those 3 dimensions, we can resist any exerted force and torque kinematically due to non-penetration limits. Now, in the other 3 dimensions, we can move, and we saw it slip, so we know it can. And what prevents motion in these directions is friction. And so the question is, how much friction do we have? Well, for a planar joint like this, we can capture the space of exerted wrenches provided by frictional support by something called the limit surface. And because we're dealing with a planar case, we can construct the limit surface either using something called the ellipsoidal approximation or the generalized friction cone. And to kind of better understand what the limit surface is, we're going to dive a little bit more into the ellipsoidal approximation. So if you have a planar joint, and we're going to assume you have uniform pressure distribution and isotropic friction, then you can capture the space of wrenches that a frictional support provides by an approximation called the ellipsoidal approximation. So you can capture the space of wrenches as an ellipse. And kind of looking at a planar grasp in a little bit more detail, one way you can think about this is that if we have an exerted wrench and if we transform it into the frame of the hand, if the exerted wrench lies within the boundary of the ellipse, we say that we have enough frictional support to resist that exerted wrench, and our objects are not going to move relative to each other. Effectively, we have enough friction wins. But we can imagine there are different grasps where when we transform the exerted wrench into the frame of the hand, if that exerted wrench lies outside the boundary of our ellipse, then we can imagine that our exerted wrench overpowers our frictional support and the two objects move relative to each other. Now, how it moves is actually well characterized, but we're not going to use that just yet. We're just going to check, do the two objects move relative to each other? So summarizing, so the limit surface is in 3 dimensions. As I mentioned, we're dealing with a planar case. And for isotropic friction, it's characterized by this matrix A. A is parameterized by our grasping force N, our friction coefficient mu, our area of contact R, and an integration constant C. So it means that we assume that all of these quantities are known. Later on in the talk, we'll think about how we can relax this assumption. So to use the limit surface, we effectively do a rigid body transformation to transform our wrench into the frame of the hand, and then we evaluate, does this vector lie within an ellipse? This is an incredibly efficient computation. So if we want to evaluate if our frictional joint due to contact is stable, we're using a combination of kinematics and friction to assess these type of joints. And kind of summarizing all together, we now have a way of characterizing for each of our joints, can it resist the exerted wrench? Now in this case, and this maybe is not a surprise, our constraint is not satisfied. We actually saw this before. This is the case where our bottle slipped, and our models guessed that ahead of time. I made the robot do it even though I knew it would fail. So in this case, what I want my robot to do is that I want my robot to find a new strategy that constructs a new kinematic chain with a new series of joints that is stable and where our constraint is satisfied. So summarizing from this section, we captured, how do we capture if the constraints that exerting force imposes on a robot's decision making. We took these kind of intuitive notions of, is the robot strong enough, and quantified it mathematically. And while I walked through a couple different types of joints and a couple different models, it would be fairly easy to swap in other models. There is a 60 version of the limit surface if you are so inclined, and so you could always consider those. Okay, given that we have these models and these constraints, the question is now, how do we plan with them? And so in order to answer that, I'm going to make concrete some things I was vague about at the beginning. Because I've been talking about that we want a sequence series of actions. I didn't define an action, and none of you called me out on it, which is very polite. But now I would actually like to define that. So I'm going to consider an action as a parameterized controller. We have some controller that we are executing on the robot and has parameters. For example, here is our place action. And you can imagine it's parameterized by things like the grasp and the placement pose. And if you're curious, it is running a joint space and grasp controller. Now, we're going to characterize our actions by two things called preconditions and effects. Preconditions are what needs to be true about the world in order to execute that controller. So you can imagine for the place action, a precondition is that our placement pose has to be collision-free. And then we'll also characterize it by its effects. The effects are what are the resulting changes to the state as a result of running that controller. You can imagine an effect of placing is that you are no longer grasping the object. And these are both characterized in PDDL. So this is one action. We can characterize kind of a whole set of actions. Here's an example of the move action. Here's an example of the push twist action. I want to call special attention to the push twist action because it is an action that exerts force. And so what we say is that a precondition for executing this action is that the forceful kinematic chain throughout this action has to be maintained. And so that is how the constraint gets baked into the system, is that it is a precondition for any action that exerts force. I'll also note, if you're curious, that the controller we use to exert force is a Cartesian impedance controller. I'm happy to talk about that at length if anyone wants to. Okay, so given that we have kind of our sequence of actions with this parameterization, our goal, our task and motion planning objective is that we want to find a sequence of actions. We want to find the parameters of those actions subject to constraints. And those constraints are captured in our preconditions and effects, and they relate to both force and motion. And so there are many task and motion planning solvers, but I'm going to talk about my favorite / the best one, which is Padiddle Stream. So Padiddle Stream is a task and motion planning framework. I think it also, in addition to this is what we use, I think it gives a good illustration of kind of what are the challenges of task and motion planning. But to use Padiddle Stream, you have to specify a series of what's called streams. And streams can do one of two things. One is that they can generate possible instantiations of your action parameters. Now, your action parameters are often continuous, so you can think of these as samplers. And so you could have streams that, for example, sample grasps or sample forces. You can also have streams that themselves run entire planners, and so you could have streams that run a motion planner to sample a trajectory or generate your impedance parameters. Our streams, in addition to generating possible instantiations of our action parameters, they can also evaluate constraints over our parameters. So for example, we've got streams that evaluate our forceful kinematic chain constraint, or evaluate if a path is collision-free. Now I'll note that the algorithms, the implementation, the models of this, they could be analytical, they could be learned, they could be some combination, you can kind of put anything in here. I'll also note that in defining a new domain, such as considering manipulation that reasons over force, the majority of the work is in specifying the samplers, because that is where all of the gory, messy details come in. For me, this also highlights that task and motion planning as a computational framework is a way for bringing all the pieces together, but you do not get away from having to solve all of the beautiful physics and geometry problems. Okay, given that we have these streams, we're going to start the algorithm by it's going to generate some instantiations of our streams. So it's going to sample paths and grasps and wrenches. And it's going to take that along with a specification of our actions, our start state, and our goal state, and hand it off to a PDDL planner. This is a domain-independent discrete planner that is going to search for possible sequences. We specifically use fast downward. What the planner is doing is checking, given the samples that I have, can I find a satisfying sequence of these parameters and actions to satisfy my task? And it's basically going to keep searching, doing this sampling and searching until it successfully finds a plan. There are details in the paper about, in Kaylin's paper, about how it's done intelligently. And I want to highlight that this kind of sampling and searching is doing the kind of problem solving that we started the talk with. This is what is doing the can we satisfy our constraints? We will keep sampling and keep trying to satisfy all these constraints. The output of Padiddle Stream is that we then have a plan that is a sequence of our parameterized actions. And so here we can see it in action. Opening the childproof bottle. This is the exact same framework that was used to generate the video at the beginning of the talk in order to cut the cucumber. And it's because we've empowered our robot with kind of models in an action space, the robot can then use that to kind of do decision making across a variety of different tasks in the same framework. Not only can it solve, this task in a particular environment, but it can solve this task in a variety of environments. So here, I've asked it in every case to open the bottle, but the objects are in different places. There are different objects in the scene, and so the robot is reasoning over, all of different, infinite number of strategies that it can use. Sometimes it leverages the device, sometimes it relocates things, sometimes it uses the tool, and it's able to kind of find this rich set of things, which for me is necessary for the robot to generalize, because I want it to be able to do this in kind of many different environments. I'll quickly note that in addition to kind of cutting cucumbers and opening bottles, we also demonstrated this in the context of twisting a nut on a bolt, kind of a more classical tool use task. We didn't have a bimanual setup, so I apologize for this being in simulation. But I did want to demonstrate that you can do this type of uncoordinated bimanual manipulation just as easily. So summarizing from all of this, we kind of captured, what is the constraint required in order to reason over exerting force, and then integrated that in the context of a task and motion planning framework in order to solve these complex manipulation tasks. And before we move on, I want to take that quick detour that I promised, which is that, if we think back to the task and motion planning framework, as I kind of alluded to, the heart of this is really the streams, is the planners. And so while I just walked through how you can reason over exerting force on the task and motion planning level, you could also imagine having individual streams that reason over force. And to kind of demonstrate that through example, I want to take this quick detour into regrasping and thinking about in-hand manipulation as an instance for where you can reason over force in kind of a different context. So let's say that I want to spell out a funny word. And because of the environment, the space of initially available grasps does not overlap with a set of grasps that allow me to achieve the task. Now, yes, this is a little bit contrived, but I would argue the need to change your grasp happens a lot throughout the... I'm sorry, it was beautifully designed. Sorry, Alberto. That this happens a lot, if you open the totally not messy toolboxes in MCube, that you may have to pull a screwdriver out from the tip and then change your grasp in order to tightly grasp the handle. And so there's been a lot of work in manipulation on thinking about how you can change your grasp and regrasp, including work by my own sister. So there's been a lot of beautiful work. Today we're going to look at one particular instance of regrasping, and in particular we're going to think about how we can change our grasp in hand by pushing against surfaces in the environment. And so here we're going to change how we're grasping our T-shaped object by pushing against a phantom hand in order to spell out, mittens or something. So our planning problem here, to make it concrete, is that we have some initial grasp, we have some final grasp, and we know where in the world we can push against. And our planning problem is that we want to find where and how to push against in order to move our object in hand from our start grasp to our final grasp. Now, the kind of fundamental constraint or difficult part of this problem is capturing, for a given pusher, what is the sequence of motions that are reachable. And it's because due to the underactuation of friction, for a given pusher, there are some motions that are possible and there are some motions that are not. And so we have to map out what is the space of reachable motions for a given pusher. Now, in 1986, my academic brother and grandfather, Matthew Mason, defined the motion cone as the set of feasible motions that a rigid body can follow under the action of a frictional push. Great! This is exactly what I said we wanted. Are we done and can we go home because Matt already solved it? Well, not quite. Brother left us some work. Because the motion cone as originally captured, it really only captures this planar case where you're operating on a table. And so it does not capture the case we show in the video where we're acting in the vertical plane, and so we have the effect not only of the pusher, but also due to gravity, and our support surface is not a table, but our grasp. And so one of the main contributions of this work is extending this notion of the motion cone from this setting to all of these settings, effectively generalizing this fundamental concept within manipulation to consider a broader set of external forces and support surfaces. And so we want to construct the motion cone. This is a set of feasible motions that we can achieve under a frictional push. And while I'm not going to go into all of the details, as beautiful as they are, this ends up using a lot of the tools that we've talked through before, like our ellipsoidal approximation of the limit surface and our generalized friction cone, we're effectively going to combine all of these forces and then solve for the resultant motion. And this resultant motion is our motion cone. This is the set of feasible motions. And so a motion within this cone corresponds to a motion that we can achieve under our frictional push. And again, I won't get into the details, but for any model, we experimentally verified it with thousands and thousands of pushes. The motion cone does hold fairly well. But given that we have this approximation and we trust it, we can now return back to our planning problem. And you think of if we're starting at initial grasp for a set of available pushers, the motion cone defines what is our reachable set, what is our set of feasible motions. And so we then frame this as a sample-based motion planning problem. We specifically use TR or T-star to kind of map that reachable set forward in order to plan for a sequence of pushes, in order to finally find, come on RT, go, a sequence of pushes that moves us from the initial grasp to our goal grasp. And we can see this in action. Here, the robot directly pushes to the side. But if we then swap out our fingers for slippier fingers, the robot knows that it has to both push down first before pushing to a side to account for the force of gravity that's going to slip as it does that side push. I'll note that we're giving the planning times on the side, and it's able to plan these in kind of fractions of a second, and this is in contrast to a previous method that had to solve a gross inverse dynamics problem and took significantly longer. We do assume that we know the object geometry, but we are able to handle things that are non-convex. So summarizing from this, we extended the notion of the motion cone to consider a broader set of planar tasks. We kind of captured all of the messiness of friction and gravity and all of that within a closed form set. And given that reachable set, we were able to apply in the context of a sample-based motion planning problem in order to enable regrasping. And if we go back to kind of where we started, we can actually think of this entire work as basically serving as a planner that can fit as a sampler within the context of our task and motion planning framework. That all of this work gets us like a new skill unlocked for a robot that we can now sequence with all of our other skills. So summarizing again, a little bit bigger picture, across this we've seen how to reason over forces both at the task and motion planning and at the planning level. And before we move forward, are there any kind of quick clarifying questions? Everyone always wants to move on to uncertainty. Okay, let's talk about uncertainty. So in this case, we were thinking about models, and what I now want to think about is if we move into messier and messier manipulation, how can we get our robots not only to reason over those constraints related to geometry and physics, but to do so when we have uncertainty about both of them. And we're going to start off by thinking about, in the context of our forceful manipulation, how we can make robust decisions in the context of uncertainty about our action parameter, about our state parameters. And so to explore this, we're going to return back to our cutting domain that we started with. And although there are an infinite number of ways for you to grasp the knife, for right now, we're going to consider 3 different grasps as kind of illustrative examples. And we're going to only consider the downward slicing motion of the cutting action. Now, given our forceful kinematic chain models, and we know what the object is, for each of these grasps, we could evaluate, is our forceful kinematic chain constraint satisfied, and check if all of our grasps are stable. And if we're cutting an object that has low force requirements, like an unpeeled banana, then, for all of these grasps, we can say that it is stable, and we're able to cut through the banana in all of the cases. But let's consider something that has higher force requirements, like a unpeeled banana that I did not peel for the robot. So in this case, while the grasp was just barely stable because there's a lot of variation in bananas, as one can tell you, that maybe this grasp is not stable. It was all planned, Tomas. This middle grasp is stable most of the time, and this far grasp is easy peasy banana squeezy. It can cut it all the time. But now, we're going to, move past bananas and think about something that requires even more force, like our old friend the cucumber. And in this case, these 2 grasps that are grasping from the top are not able to cut through the cucumber. But the grasping from the side is. If you were really paying attention in the very first video, you would have seen this coming. Fun. Okay. Now, while I'm showing here one video for each food and grasp item for each of our 9 conditions, I will say we repeated this 10 to 15 times for each of the 9 conditions. So not to brag, I've had a lot of meals prepared for by a robot. They're just like not ones my parents would approve of for dietary reasons. So this is why I have to keep going. But if you looked at all of those videos of us cutting and you didn't watch the part of the video of me eating, then you might come to the conclusion that this grasp on the side is the best. Because you might say that it was able to cut through the largest majority of items. And we've talked about enabling a robot to do a lot of this reasoning, but if this is always the best, then like, why do the reasoning? Why can't we just always go with this dude? And thank you, straw man person. But that is not always the case for 2 reasons. There's not actually one grasp to rule them all. And that's because A, this is the strongest grasp for this particular task, for this particular wrench. That wouldn't hold true for every possible wrench. But more broadly, it's not just about being strong enough. We have to consider both geometry and physics. And if you look at this grasp, because of the geometry of the panda hand, which is quite fat, that this grasp is actually only possible and only collision-free if the thing that you were cutting is elevated. That is why all of our cutting boards were very thick. And so you might imagine that there are scenarios where you would prefer this middle grasp because it might be strong enough and it can reach a more confined set of spaces. And so it might be a better trade-off. Now, there might be times when you're cutting a cucumber and you truly need the strongest grasp, in which case your robot would need to plan a sequence of actions to relocate the object somewhere where you could reach and use this grasp and it being collision-free. So the question is, if I want my robot to be able to make this kind of reasoning, to do this kinds of trade-offs, that's not only capturing kind of our geometry and physics, but reasoning over uncertainty and making choices about what is the most robust choice, how do I enable that? So we're going to think about that by enabling robustness, by thinking about robustness as a cost. And what I mean by that is that we're going to take our forceful kinematic chain models, and we're going to take the parameters of our models, like the area of contact, like the force required, like the coefficient of friction, like all the things I said we assumed we were known, and we're going to perturb those. You can think of that as capturing a bounded amount of uncertainty in those parameters. And across our perturbations, we're going to count how many lead to a successful forceful kinematic chain. This gives a probability of stability over perturbations in our physical parameters. And if we take the cost of an action to be the negative log of this probability of stability, then what we can say is that by minimizing this cost, we're going to maximize plan success likelihood. And within a framework like Pareto stream, we can implement additive action costs. And so we can say that the cost of a plan is the sum of the cost of our actions. And then we can ask our planner to find a cost that is within some permissible threshold. Yeah? Yes, please. Hi, Bill Kid. In the examples, for the illustrative examples for cutting, I was only thinking about the downward motion, which you're correct is only half of cutting, because we frame cutting as downward and then slice. When is computing all of these, it is considering all possible motions. And so it is not constrained to just that. Other questions? OK. The benefit of this and why I like thinking about robustness as a cost is because I don't want to have to tell my robot what is the most robust choice, what it should do. Again, it is the robot's responsibility to do that reasoning. And by framing robustness as a cost, the robot can then balance all of the constraints that it has to satisfy alongside the cost and kind of make its own decisions, which is necessary for the robot to generalize to a lot of different environments where it can cut bananas everywhere. OK, so thinking about robustness and this kind of conformant planning is one way to handle uncertainty, but it's certainly not the only way. And for what is the last technical component, I want to think about a different framing of uncertainty. And particularly, we're going to think about action uncertainty in the context of dynamic manipulation. So throughout this talk, we've kind of dealt with a lot of different actions. We've been building up an action space. And a lot of these actions we can model either kinematically, like move, or quasi-statically, like the regrasp manipulation enabled by our motion cones. But I want to push my robots further, and I want them to be able to consider dynamic actions. For example, I want my robots to be able to kind of topple and push things, and this is because if enabling robots to do this in kind of a dynamic, non-prehensile way, our robots can expand its reach, it can manipulate things that it can't directly grasp, and it also, in some cases, perform manipulations more efficiently. And so in the same way that I have a move action, which takes me from a start configuration to a goal configuration through a series of motions, I want to add to my robot's repertoire a dynamic non-prehensile move, a DNP move, that allows my robot to manipulate an object from a start pose to a goal pose through a series of these kind of bounded non-prehensile dynamic actions. So we're going to think about how we can enable this. So I've touted these actions as being really helpful, but we also must face that they are highly uncertain. So this is the same action repeated twice, and we get fairly different results. And so the question is, how do we model this type of action? And throughout this talk, I've really leveraged a lot of models from classical mechanics, but argue for these types of dynamic manipulations, like this kind of fast pushing style, there don't quite exist efficient closed-form good models of the dynamics. That's okay. Classical mechanics is not our only source for models. In this case, we're going to opt to learn a model. What I mean by that is for an action, an object, and a surface, we're going to gather a sparse amount of demonstrations or examples of our action executing. We're going to take what is the resulting outcomes. We're actually going to factor by face, and we're going to learn what I'm going to call outcome volumes. And outcome volumes capture what is the space of possible resulting configurations having taken that action. I will note this is not a probability distribution because that would require way more data to characterize, and I am not willing to gather that much data. So we're only going to capture what is the space of possible configurations. I'll note that the outcome volumes, while they're conditioned on several things, we're going to assume that they are positionally independent, and while we gather them in a space without obstacles, we are able to handle environments with obstacles with some limiting assumptions, and I'm happy to get into in more detail. Given that we have this very uncertain model of our object's transition function, we're going to frame that DNP move planner as a contingent planner. And what I mean by that is that we're going to ask the planner to generate a sequence of possible actions. The robot is going to execute the first action, it's going to look, and then repeat. This is to handle uncertainty. We're basically going to do this in a reactive, and we're going to close the loop. Now, ordinarily, I might jump into thinking about, okay, how can we generate this action sequence? But this framework of contingent planning actually makes a pretty critical assumption, which it assumes that the robot can keep looping and trying and going over and over again. It assumes that you can keep planning. What if your robot knocks the object off the table? You know, what if your robot pushes something into a corner where it can't get things out of? Both of these are instances of actions that lead to dead-end states. Dead-end states are states from which it is impossible to achieve the goal, and that could be, you could be at a dead-end state because there are no actions that are possible, like it's out of reach, or there are actions that are possible, but none of them are going to get to the goal. You're just going to stay there. It is the Hotel California of configuration space. And so what we want to specify is that, you know, if we're going to do this type of reactive planning, the constraint that we need to maintain is that we need to move towards the goal. Yes, we want to plan for sequences towards the goal, but we have to make sure in doing so, we never take an action that leads to a dead end. We never do anything that is irrecoverable. Stated another way, if we never do anything catastrophic, we can keep kind of planning and looping over until we get to the goal. And so this is our planning problem. How do we generate sequences of actions, particularly with a focus on never hitting a dead end? Now, I have framed planning with uncertainty under dead ends in this context of dynamic non-prehensile manipulation because I think it is a beautiful illustrative example of it, but this has come up in a lot of other contexts across controls and motion planning. A lot of these contexts assume that either you have continuous dynamics or you have more certainty about your dynamics, or they assume you have a discrete state space. And so these make it hard to apply directly in our context where we have both non-determinism and a continuous state space. And so what we're going to leverage is the fact that we're going to leverage our outcome volumes to continuously characterize our dead ends areas. To give the intuition of that in the simplest way possible, we can think of if our outcome volumes capture the space of possibilities, that if some of our possibilities end us up in a bad area, then do not take that action, robot. And that's going to be the kind of intuition of a planner that if you're dealing with uncertainty and risk, I want to enable my robots to be guarded. And yes, that is the algorithm, and of course the name of the algorithm. You didn't think we were going to get through without an acronym, right? Come on, guys. This is guiding uncertainty, accounting for risk and dynamics. And before jumping into the algorithm, I'm going to discuss the environment in a little bit more detail, establish some important assumptions. We'll get into the algorithm, and then incredibly preliminary results. So to start off, we're going to consider that a robot is operating on a surface. It is trying to manipulate a target object to a goal pose, or more generally, a goal region, again, through the series of our dynamic actions. We'll assume we might have obstacles in the world, and you also may have objects that you're not allowed to interact with. You can imagine this being a glass vase, that if you contact it, you have also hit a dead end because you can't put the glass vase back together. So this is our environment that we're operating in, and we could represent the configuration of our target object in SE3. But we're going to leverage the fact that we're operating on a tabletop, and we're going to consider a factored configuration. This is to say, we're going to represent our configuration in 3 parts, first of which is, for our object, what face of the object is in contact with the surface. For example, if you're dealing with a rectangular prism, leveraging symmetries, you can imagine there are 3 different faces that could be in contact with the surface. In addition to the first surface, we're going to characterize the configuration by a discretization of our planar orientation, and then our continuous planar position in XY. I'm going to define the mode as being what face you're in and the discretized orientation. Both of these are discrete, and so we have a discrete number of modes. And the reason we're doing this is if you fix your mode, then your configuration space is then your planar position, which is in R2. And this is going to be critical for making a lot of our computations later on efficient. This also means I can give kind of the planar visualization of our environment, and I won't get into all the details of how this is directly computed, but I'm happy to talk about it at length. The last kind of critical assumption that I want to mention is that unlike in our task and motion planning context, for this particular planner, we are going to assume we have a discrete number of actions. So we have a discrete action space, a discrete number of pushes that we're trying to sequence. Okay, given this, let's jump into the algorithm and see how we can kind of encode that intuition algorithmically. So I'm going to visualize our algorithm in the components as we go, but I'm going to explain the algorithm effectively in 3 parts. First, we're going to construct 2 data structures. One is our action regions, and then our danger zones. Our danger zones are going to capture what our dead ends are, and then we're going to use the danger zones to guide our search, effectively saying that our search should never enter the danger zone. So, starting off, I'm going to visualize this as we go, and we want to compute first where each of our actions are feasible. Again, we have a discrete action set. I'm going to describe an action as being feasible if the robot and the object are collision-free, if the object is stably supported, and if the action is within the robot's reachable workspace. This is effectively capturing what are the preconditions of my action. Now, I won't get into the details, but the way we compute this is we actually compute what is infeasible, and then we take the complement, and then the union, and then you intersect it over, and you basically use every primitive operation over polygons that Seagull has. And the result of this, computational geometry solves everything. The result of this is that we can effectively map our space into where each of our actions are feasible. And so each of these polygons corresponds to a set of different, subset of different actions being feasible. In addition to now, for any particular configuration, I can query what is the set of available actions. This also defines something that is critical for defining our danger zones, because this defines where there are no actions that are feasible. And so if there are no actions that are feasible, this is a dead end, because if we're not at the goal, there's nothing we can do. We also compute that at dead ends by computing a reachability graph over the regions and computing which regions have no path towards the goal. And combining these together, this is what gives us Z0. Z0 is our kind of base zone. This captures our dead ends. If our object at any point ends in zone 0, game over. So we want our planner to be able to avoid Z0. In order to capture that, we compute where taking an action would lead us to zone 0. We do that by taking what is the preimage of zone 0 over under each of the actions. This is where the positional independence of the outcome volumes is particularly critical. And this is what effectively capturing where are there actions where taking that action has some possibility of ending me up in the dead end zone. those are risky, and so I do not want to take those actions. Yes, Russ?
Does this mean action reachability being learned is like in a polytope as opposed to a deep neural network?
Yes, it produces, yeah, the outcome is a polygon. Yeah. And that's actually why we factor over the faces, because it's got to be in the same configuration space of R2. Okay, so we compute our preimages to tell us what are risky, and then what we can do is kind of recursively say that if you are in some point where all of your feasible actions are risky, then you're kind of doomed. And so we define that as our subsequent zones and kind of back up your areas of risk to define each of our subsequent zones where you only have risky actions. And so these are places you want to avoid. I will note that action regions and danger zones are computed for each mode in the configuration space of the object. As I've established, that is in R2, and so we do all of this using Minkowski sums, and because it's in R2, it is efficient. That is why we had to factor our configuration space. Okay, given that we have our danger zones, we can now kind of leverage them within our planning and think about how can we plan towards the action avoiding these danger zones, and we know if we avoid them, then we will not hit a dead end, and then we will succeed in our planning problem. Within the thesis, we discuss a couple different sample-based motion planning methods. I'm only going to overview one that takes inspiration from PRMs, probabilistic roadmaps. So offline, we're going to build a graph. We're sampling vertices, avoiding the danger zones. We define edges between two configurations if based off an outcome volume is possible to reach that configuration, but we do so only if that outcome volume avoids danger zones. And so, for example, this edge is okay, but this is not because it could get us into danger. Again, we're basically constraining the construction of our graph such that you never go into danger. This is how we build our graph, and once we have this based off this construction, the fact that we've done so in a fairly guarded way, we can now perform that contingent planning strategy, again, knowing that we will never hit a dead end. And so we generate a plan, we execute that first action, wherever we end up, we add that configuration to our graph, and we keep going. Sometimes when searching for a plan, we allow the planner to augment our graph as we go. So summarizing guard in perhaps the pithiest way possible, the algorithm proceeds by defining where can I take an action, or is it a bad idea to take those actions, and then how do I plan accounting for that? So I'm going to demonstrate guard again in some very preliminary experimental results, all of which are in simulation. We're going to demonstrate on a couple different environments, which I won't get into the details for, but we're going to compare the algorithm I just walked through against a baseline that basically does not compute danger zones. And so it constructs that graph without those guardrails, and so it is the unguarded version. I'll note that our results, I'm going to split into three categories. We can either succeed, we can fail by hitting a dead end, which is DE, or we can actually hit a timeout. And this is because we limit kind of the number of steps the contingent planner can take and the number of graph augmentations. So it is not failing because the robot gave up, but it is failing because I, the programmer, gave up and I'm tired of waiting. And so if we look across our planners and our environments, what we see is that guard succeeds in never hitting a dead end and succeeding more so than the baseline, which does occasionally hit a dead end. I will say that doesn't always succeed and that it does occasionally time out, and I think looking into that is an area for kind of more analysis. Very briefly, I'll comment on the computation. We split into offline and online time. Offline is computing those structures and computing the graph, and online is both doing that search and occasionally augmenting the graph. Unsurprisingly, because the danger zones are the most computationally expensive part, the baseline is significantly faster, both online and offline, than guard, but there's definitely further optimizations to be made here. I'll note that these results are very preliminary, and if you're interested in seeing more, come back next year when we do this all again. But summarizing from all of this, in this case we framed briefly dynamic manipulation planning as an instance of planning under uncertainty with dead ends, and to handle it we proposed guard, which basically continuously characterized where are dead ends and then constrained our search based off of that. I also make kind of a note here that guard kind of adopts a different planning philosophy than we often see in motion planning, and that we're not optimizing for anything. There's not a cost or a reward. Instead, we are just constraining ourselves to basically staying alive and never dying. Is the idea that if the biggest constraint is that you can keep acting, and so guard takes the philosophy of if you can keep acting, if you never do anything catastrophic, then you can always keep trying and you will be okay if you can keep trying. If you want to apply that outside the context of dynamic manipulation, that is an exercise left to the reader, as they say. So it's kind of summarizing across all of this, kind of wrapping up the technical component of this. I have always wanted to and focused and will continue to focus on kind of enabling robots to perform these type of long horizon manipulation tasks. It is really my dream to get robots to be able to cook things in the home and to kind of do these complex tasks. And I would argue that in order to accomplish these types of tasks, it is fundamentally critical that we reason over both geometry and physics. As Roberto highlighted, those are often separate, but I think it's critical that you have to look at the intersection. Choices in geometry impact your physics. We saw how thinking about your physics informs the type of uncertainty that you consider. And so I think it is critical to really sit at the intersection, to look at all of it at the same time, as difficult as that is. And throughout this thesis, to kind of handle this, I propose models and algorithms. And the focus of this is that I want it to be the robot's responsibility to do the reasoning over this geometry and physics. I fundamentally want to be lazy and make it as the robot's responsibility to decide how it's going to act in the world. I think that is necessary for my robots to generalize and kind of act all around. So with that, that's going to close the technical component, but there's kind of one more piece of business that we have to handle before we move into questions. Any immediate questions before? I'll do them at the end. Okay, so there are two people without whom this work could not have been done. These two people are my biggest champions. They're the people who are most excited by my robot videos. They're the two people most likely to ask me, when are you writing your next paper? And I am, of course, referring to my parents. So my parents, yeah, Tomas has never asked when I'm writing my next paper. He knew it wasn't him. So my parents have given me an infinite amount of love and support. They have provided me with every privilege they could in order for me to get here. I know some people say that their parents served as their role models or mentors, but my parents really were my first mentors. This is my mom and I pair programming together. We're doing lab use, don't tell anyone. But my mom really was my first kind of technical role model, and it's from her that I get the push to just keep going, to never stop. You have to keep going. And I definitely inherited that from her. From my dad, I think I inherited most of my academic tendencies and my habit of putting jokes in talks. I am really delighted that I will be able to earn both of my dad's honorifics of doctor and professor, and I hope he is proud of that. And while we have, a dozen more slides to get through of acknowledgements, none of this would be possible without my parents, and this thesis is dedicated to them. One of the gifts my parents, One of the gifts my parents gave, if you don't know, that I'm one of 4 children. And so I'd like to thank each of my siblings. My older brother, Ben, as an older brother, really kind of lights the way. And to kind of show it off, in my acknowledgement of him, I would like to use him at his thesis defense with his singular acknowledgement slide. Is this little sister energy? Yes, but this is what Ben expects, and he gives me kind of protective and proud older brother energy that I am so grateful for. One of my biggest influences is my older sister, Annie. Annie is, again, one of my biggest champions. I started in robotics by following her around as her assistant. She is the one who encouraged me to do undergraduate research. She is always supporting me and giving me comfort and adding the appropriate level of zaniness to my life. And finally, if you did not know, I am actually a twin. If you would like to meet the smarter, cooler, and taller version of me, I would suggest introducing yourself to Sam. So growing up, I did all of my classes and extracurriculars and activities. All of it was with Sam, and Sam was always kind of pushing me to be better, and I'm still working towards that. I am so grateful for that. Alongside my family, the two kind of biggest forces that got me to grad school were first robotics. Yes, I'm a cliche. First is where I fell in love with robotics. And then also Carnegie Mellon and the Robotics Institute. That is where I fell in love with research and was trained on how to be a roboticist. Throughout grad school, I'm very grateful to have had friends who've supported me. Special shout outs to my roommate Vibha, to Neely, to Lily, to Ariana. I love you all. And I want to give a special kind of shout out and designation to Marlise Reeves, Leanne Makatura, and Michael Noseworthy. I could not have gotten throughout grad school without these 3 people. They were a huge source of support. They have supporting me when I've cried, supporting me when I've triumphed, taking me out for shenanigans. They've listened to so many rants that I am so deeply grateful for all three of them, and I love them very much. Speaking of love, I want to give a very extra special shout out to my partner, Jai Tao Liang. Gives me a lot of love and support. He takes care of me, shares me joy, pushes me to be better. I am so grateful for him. And te amo, wa'aini, anila dodila dodidui. And I feel better knowing that no one understood all three of those languages. So I'm lucky in that I've been able to be a part of two groups throughout my PhD, and the first is the Learning and Intelligence Systems group. What I love about LIS is that I think better than anywhere else, really think deeply about intelligence and what it means to get to embodied intelligence, and how to think about generalization and uncertainty in really deep ways. I will incredibly miss the rants that happen within LIS. They're a source of great support. And I want to give a special shout out to my desk mates, Kaylin, Rohan, Bamjun, Clement, Sahit, Shaolin, Jayuan, Ilun. We've moved a lot. I've sat next to a lot of people. I'm actually very, very grateful for that. In addition to LIS, I'm also very delighted to be a member of the Manipulation and Mechanisms Lab at MIT. The beautiful thing about MCube is that people work on a lot of different things. We're all kind of united by this idea of thinking about contact deeply, and that always leads to kind of delightful conversations. I think there also must be some kind of personality screen, because MCube is full of just like people who are up for a whole lot of nonsense. And that creates for a really delightful environment. I want to give a special shout outs to my desk mates, Nikhil and Nima, Neha, Orion, and Anthony. And with MCube kind of drawing to a close, I am so honored to have been a part of it. Now within this, there are a couple lab mates that I have to give particularly special shout outs to. First, I want to thank all of the students that I was able to work with: Danny, Ashwin, Greg, Rachel, Annika, Tarang. Thank you for letting me work with you. You all taught me so much and brought so many interesting ideas, and you gave me so much grace as I learned how to be a mentor with you. I want to give an extra special shout out to Teresa and Lisa. Is Lisa in the room? No, because she's setting up, because she's great. So Teresa and Lisa are absolutely the best admins. They have spoiled me rotten, and I am so grateful for all of their help throughout the years. I am not a mechanical engineer. I'm just not. And so I am so grateful to have had access to beautiful mechanical engineers, Elliot and Ian. Not only did they help me fabricate, I told you MCube was zany. Not only did they help me fabricate things, but they let me pester them with so many questions, and so I was able to learn through them. Two of my biggest mentors throughout, especially the beginning years of PhD, were Nikhil and Kaylin. Nikhil is kind of my closest academic brother in so many ways. I would love to tell you how hard he had to work to teach me mechanics, but he would have way more fun telling that story, so you can ask him. I think I owe him $10. I also want to thank Kaylin. Kaylin really took me under his wing and really teaching me all he knew about task and motion planning. I'm really happy to be the first and primary Priddle Stream descendant and disciple. Throughout MIT, I'm really happy that I got to engage in kind of learning how to teach, and I want to give kind of a special shout out to the teaching and learning lab, specifically Ruth Ann and Ben, for really framing how I think about teaching. I also want to give a shout out to Russ. I really learned a lot TAing with him. He also, he recruited me to come here. He's supported GWork. He's always had an open door for when I've had questions. I really don't know what I did to deserve so much support from Russ, but I've stopped questioning it, and I'm very grateful for it. Over Zoom, I'd like to thank my committee member, Dimitri. I have loved Dimitri's research since as long as I was a researcher. It's also thanks to him that I have one of my favorite moments of my PhD when he said, "Are you really doing Minkowski sums in 2023? Yes, I am. It's efficient in R2. So Dimitri, thank you so much for your feedback. Next, I want to thank Leslie. Leslie is not my official advisor, but Leslie is who we go to when our trio gets stuck. And so she's our official bailer-outer. I have so many example instances, but I think my favorite is I spent days, if not weeks, thinking over, how do I frame my work? This was in context of the job search. And I had many discussions with my advisors, and we were going over, thinking about terminology and phrases and kinematics versus dynamics versus mechanics versus contact versus forces, and like, what is the best way to phrase this, and agonizing over it. And then I go to Leslie, and in about 10 seconds, she goes, physics? I think you mean physics. And so I have so many instances where I get stuck and I'm singing for days, and then in 10 seconds, Leslie solves it, and that is such a gift, and I am so grateful for her. If she's curious, this is when Leslie gave a group meeting talk by pulling out her transparencies from an old talk, and I'm so glad I didn't have to do this talk over transparencies. But thank you so much, Leslie. And so lastly, I want to thank my 2 advisors. And first, I want to thank Alberto, and to do that, I'm actually going to tell a story. This doesn't put me in the best light, but it's not about me, it's about Alberto. So I was in my 2nd year, and for reasons we won't get into, I was going through a particularly rough time, and several of my colleagues and friends noted that I was particularly bimodal, that I was either friendly and talkative or incredibly grumpy and no one could deal with me. And so Alberto does this lovely thing where we have annual reviews, and in the annual review for that year, I told him that I thought that I should kind of get my grumpiness under control and work to put up kind of a veneer of being friendly. And that it would be more professional to kind of put up the face and try to be more friendly. I thought Alberto would either agree or kind of have no comment. And instead he furrows his brow and starts to get angry because he goes, no, you should not have to hide and put up a face. If you're upset about something in particular, I'm happy to talk about that. But no, you should absolutely not feel like you have to put on a friendly face, that you have to be kind of nice to everyone, and that if you want to be grumpy, you should be grumpy. And it is one of the most empowering things I have ever heard. Alberto has always believed in me when I don't believe in myself. He has always said yes, even when maybe a few times he shouldn't have. He has taught me how to think about manipulation deeply, how to communicate clearly, the importance of good writing, what good writing is, how to think about contact in a critical way, the importance of an illustrative example, as long as the illustrative example I picked was not planar pushing. And so I am so grateful to have been Alberto's student and that he said I will always be his student. And to everyone else, if at any point you felt I was grumpy during my PhD, it's kind of Alberto's fault. So thank you so much, Alberto. And lastly, I want to give a thanks to Tomas. You can play a game here, which is match Tomas to the student whose defense he's standing at. Or answer the question of what is a plural of Tomas? What is a group of Tomas called? So if you would have asked me as an undergrad which researcher was I most intimidated by in the world, the answer would have been Tomas. And that's because the people who I got advice from got their advice from Tomas. And in some ways, I was correct to be intimidated by Tomas because his breadth of knowledge and depth of knowledge is frankly insane. And he has taught me how to think deeply, how to think about what are the important problems, how to think about uncertainty and generalization in critical ways, how to communicate clearly, and how to think about manipulation in the context of kind of different domains. Again, as long as that domain is not planar pushing. So as right as I will have to say, I'm sorry, Tomas, I was incorrect to kind of be intimidated by Tomas because he is so warm, he is so empathetic, particularly if you're dealing with robot debugging problems, he understands it. And I have loved kind of our tangents and our support. If Tomas is going to give you critique, it's going to be wrapped up in a joke. So he's going to say things like, you're behaving like a random tree, so we need to add some goal bias. Or, you are making progress, but only in belief space. I'm getting laughs for your jokes. And so I am so grateful to Tomas for all of our tangents, and I look forward to commiserating about students who don't get our references. And so with that, there's kind of one more thing that I have to thank, and that is my robots. I love my robots dearly. They are a source of joy. They are a source of frustration. I've gotten my blood, my sweat, my tears, my happy tears, my sad tears. I don't see that changing anytime soon, and I'm actually pretty happy with that. And so with that spirit, I want to end this part of my defense the way, honestly, a plurality of my advisory meetings have ended, which is with the phrase, damn the torpedoes, full steam ahead. We won't stay on that slide.
All right. Well, thank you. Who wants to go first? wants to take on the challenge of the first question?
Going
Okay,
way over.
banana person. Any comments, any reactions to violence against bananas?
Yeah, I felt a little threatened, honestly.
Again, in Patrick's defense,
But-
I did explicitly request this, so he was
Yeah.
doing a beautiful lab mate favor.
Yeah,
I want that
that's
on the
true. I
record.
wouldn't have shown up like this if that was requested. It's not like I came here just to frustrate Tomas or anything like that. Anyways, so you talked a lot about the Minkowski sums and that being tractable, in
R2, yeah.
But so the question I had was like a natural kind of extension that seemed like, oh, well, if you have these volumes, if you did have a probability distribution, then you could start thinking about like, well, maybe there's a small amount of probability that you go off the table, but most of the time you're on the table, so maybe this is not that unreasonable of a move. How quickly intractable does that become if you start kind of going down that path?
Yeah, so I think that's an excellent question because right now it's an incredibly conservative planner, which is if there's any chance that something could go wrong, don't do it. I will say that the level of conservatism within the planner can be controlled in that our outcome volumes capture row percentage of the data. I didn't get into the details of this. And so if you modulate that parameter, that kind of captures how conservative things are. With respect to computational, there's the question, one, of how much data would you need to gather in order to be confident in the probability distribution that you're defining, which is, I think, separate from if you wanted to do the planning characterization, which I think if you have those volumes, you may kind of do stacks and various computations, but I don't think that would be too problematic. Sam?
Don't worry, I'm on my way.
First of all, Rachel, great job. I love you and I'm very proud of you.
Thanks.
Second, not to be too controversial, but in the first half of your talk, it's interesting that you took this kind of first principles approach where you know these facts about the environment, you take physical and geometrical models, and you plan an approach to perform this action. And then in the second half, you take a completely different approach where you say, well, there's a lot of uncertainty, so let's try to learn this from actions and not really go with the physical model. So what is stopping someone from completely chucking any sort of physical model at all and just going exclusively for supervised learning? What is the kind of the advantage of going with this kinematic approach, if you will?
Gotcha. If you can't tell, Sam did his undergrad at Berkeley. So I wouldn't say that they're entirely separate. I will agree that in the first half, we kind of had these really great models from classical mechanics. I don't know if we're hitting feedback. And I think in the cases... Oh, okay. In the cases that you have those models, I don't think you should throw them out because they're particularly powerful in order to leverage. So I would say if you have the models and they're efficient, why not use them? In the case that you do not have those models, then I think learning them from data makes a lot of sense. And I think you can also capture uncertainty sometimes in the case of learned models, but those mechanics models can also capture uncertainty. And so I don't see those as being entirely separate. In my view, it would be a combination of when you've got the models, use them. When it makes more sense to learn them, go. And that it's kind of more which makes sense in the specific context as opposed to coming down and saying there is one way to rule them all. Gustavo.
Great job.
Thanks.
A bit on the topic of learned models, I think a very common thing that happens with learned models is that they usually output learned models often output position set points for some lower level controller, and that strikes me as a sort of not fundamentally so, but kind of more geometry than physics happening there, and I think that. We can all understand that it's harder to do geometry and physics, as you've shown us, and it's very impressive. I'm wondering if you can speak to some ways in which it makes the problem easier, that if you were limiting yourself to only sort of geometric planning to achieve the same task, you might run into some trouble.
Yeah, that's a really beautiful question. So I think in some ways, if you're only considering geometry, then there are some things that your robot will not be able to do and that you'll not be able to kind of reason over that physics and you'll be handicapped in that way. And that's why I think a lot of things that since they're only geometry, there's a limit to what the robot can do. I think there's also something in that if you think deeply about, what is the environment that your robot is operating in, that informs your constraints. And as maybe a more specific example, that in a lot of this work, we were thinking about, there's not some general notion of uncertainty in kind of a vacuum that like things are uncertain and we know nothing about it, and so we have to treat it in the most general way. But if you kind of ground it in the manipulation problems, and is what is the notion, kind of reasonable expectation of that uncertainty, and then can you leverage that to plan, as opposed to saying, I don't know anything and I have to deal with that. Adi.
Any questions on this side of the room now? Just to balance.
Rachel, first of all, great presentation and great research. I'm excited to see more of your research over the years. You emphasize physics, so I'm curious about the guard algorithm. You spend 60 seconds planning, and then let's say you make a move. And let's say it's a box of milk, and I pick it up and I drink a little bit, put the milk back down. Do you have ways of not going through the 60 seconds again and using what you already had? Because now the milk is slightly lighter, let's say.
Yeah, so the computation time is not great, and some of that is just, I could be better at Python. So some of that is not fundamental. Thank you, Julia. No, I could be better too. And so some of that is not kind of fundamental to the algorithm. To get more to the point of your question, within the algorithm, we can exploring some level of caching, that if you have a plan from before, you make a plan, take the first action, and we actually don't throw out that plan. We say if that plan is still feasible, then go with it, and only if it has become infeasible would you search for a new plan. And I think there are probably several ways within the algorithm to kind of lean more into that you could prune what parts of your configuration space you're exploring, and be more intelligent in your search in order to, in this case, be more efficient, which is, I believe, what you're getting at. I will say also that the robot is not doing any kind of information gathering, and so it would not, for example, be able to online say, the dynamics of my action have changed, I'm going to adjust my models. That is a fundamentally different, although very interesting question. Dad?
So once you've sampled and you have
Hi, Dad.
and a graph has been created of possible moves, and you have accomplished that there is a path from the start configuration to the... There's probably a whole bunch of paths in that graph.
Sure.
Had you tried to optimize for something, or is that not worth the effort?
So in this case, we are only considering where your only objective is to find a path. Effectively, this is kind of maximizing your probability of getting to the goal. There was some really beautiful work within MDPs if you're thinking about the joint objective of find me a path that guarantees I get to the goal while also optimizing for finding the shortest path. This is considered both within GSSSP and SQ paired. We can talk about it over dinner, Dad. So no, we did not consider that objective. It was really just find a feasible path. And that is, I believe, some of the reasons why the robot times out, and that it's not intelligently kind of getting towards the goal. If it takes a meandering path, that is okay. And again, that's because we're emphasizing that it's not about getting there fast, it's about making sure that you never fall off the cliff. Other questions? Seiji. Nope.
First, Marlies on Zoom says amazing job.
Okay.
And I think similar to the question before, in Guard, what of the offline components of the algorithms could potentially be reused in a similar task, perhaps involving the same objects in a different initial conditions, for example?
Yeah, so the offline computation of the data structures does not actually factor in the initial configuration and could be done fairly independently from the goal. And so for different environments, that could be entirely reused. Depending on how much your environment changes, you might imagine being able to reuse some of that computation. The graph would be harder to think about kind of how that could be reused, but definitely the data structures could be. Seiji?
Thank you so much for the most wonderful dissertation talk. And I was wondering about the Guard algorithm. Can you speak to how robust your polygonal outcomes are with respect to actually characterizing the true outcome? Did you ever see them fail ever? And how would you recover if that happened?
Yeah, so there is an assumption within that algorithm that your outcome volumes capture the space of possibilities, and so it would be false negative if you fit in, if like you went outside, and we could not recover from that. How well they capture is really a question of the data collection. Again, we capture a fairly small number, but in constructing that polygon, there are some things we do in terms of leveraging symmetries and kind of robustifying that, but I won't claim that it is guaranteed to kind of capture all possibilities, and so there's definitely kind of more detailed analysis that could be done there on guarantees with respect to data collection.